general topic. We are not going in very in-depth research title here. So I'll give an introduction to the EMI and some of the mitigation methods. So okay, the flow of talk goes like this. The first introduction to the power electronics and their role in electric vehicles. Next is introduction to electromagnetic interference and common mode and differential mode components. So, and then next we will see what is common mode and differential mode components and how to measure them in inverter fed drive. Next, we will see two of the methods which can mitigate and what would be the impact in the system. Okay, so power electronics is a discipline which deals with applying solid state electronics to control, convert, and conditioning of electrical power. It's basically dealing with the electronics, how to process the electrical power very efficiently. Why we need power electronics? To fill the gap between generation and utility. Say, for example, if we have a 230 volt 50 hertz supply, and some of our appliances, say laptop requires 48 volt or 12 volt DC, so then we need a conversion efficiently. And to generate electrical power from various sources, say renewable energy sources and so on, and reconnect it to the grid. So this would be impossible without power electronics. One of the leading companies says the hidden technology that makes the modern world run. So that is power electronics. The main reason is most of the systems depends on power electronics to run efficiently and sustainably. Without this technology, electric motors would always run at full speed. No solar and wind power can be fed to the grid. These are all some of the reasons. There are n number of reasons where we can say why power electronics is very important in the present situation. And a typical power converter system will look like this figure 1. So there are input terminals and there are output terminals. Based on our needs and objectives, we can take some information from input and output and process through the controller to get what we want at the output. So the brain of the power processing system is the controller. And we have feed forward and feedback control in general for power electronic power electronic systems. So these are all the types of converters. So those who are already in this field would be knowing what is it. So orally, if we want to say, we have a direct current power supply and power and alternating current power broadly. There is always a competition between which is dominating which appliances. Because of transformer, AC has dominated the world and we are using AC in present scenario, but still some of the appliances are using DC power supply based on its convenience. So we need to convert possibly from one power to the other power. So DC to AC, AC to DC, DC to AC and AC to AC. So next, we will just introduce what is power processing system and what are the main objective in general which is considered for power electronic system. The first and most objective is efficiency. Next, we have to look at reliability and then how to reduce the size and weight in any power electronics or power processing system. So if we look at we use efficiency objective, if we want to achieve, what we can do is we can try to use the elements which are lossless. So first, if we look at switch, we are closing the switch. If we close the switch, the V of T, the voltage across the switch is 0. If we open that, it's like a normal switch. If we open that, the current through that will be 0. Therefore, ideal switch consumes 0 power. So the power loss, if we use the switch, the power loss would be 0, but it should be an electrical switch so that it would be fast enough to compared to your mechanical switch. And power processing system prefers lossless elements, inductor and capacitor. So inductors and capacitors are main purpose of power condition. Because we are using the switches, it would introduce lots of harmonics in the system. So we have to condition it by using this inductor and capacitor. Reliability aspects in general, there are n number of ways to increase the reliability. One is, say, for example, to meet some particular objective, you have fewer parts. Consider fewer parts so that the probability of failure rate would decrease. Smaller size and weight, the main reason, if you look at, the trends change, how our older TV and now how the TV size is becoming smaller and smaller. Not only TV, you take any electronic component, people would like to reduce the size and weight so that it is easy to use and operate. So one of the way to do is increase the switching frequency operation. Switching frequency is we are using the switch, so then we have to increase the switching frequency so that the magnetics and the capacitive element size goes down with the increase in frequency. This is one of the approach. Okay, these are all the practical components. So these are all the switch, semicron made switch. This one, this is also. This is Infineon, one of the famous company to make switches. So this is capacitors, electrolytic capacitor. This is toroidal core inductor, and this is normal inductor, which we use it in making the power electronic system. Okay, I'll skip this. This is just to show the benefit of the efficiency, how the power electronic system gives more efficiency than other options which we have in real life. Okay, so now we come to electric vehicle. So there are many aspects of electric vehicle. There are mechanical. Lots of people have to work on a particular product to be developed. It's not that one particular division or branch of engineering can make a product and then you can go ahead with it. No. So mechanical people, all other perspectives, the design, CAD design, and then stability, everything has to be considered to make a vehicle. So I'm going to concentrate on electric propulsion system where it deals with these components. You could see very clearly the role of power electronics in an electric vehicle. So the first starts with the charging. So you have your AC power supply with us. So first you are going to use battery as the energy storage element. So it has to be charged from AC to DC very efficiently. And then this is your propulsion unit. You have a motor which is mostly of AC motors, because AC motors are very reliable and it has many other benefits. So most preferred motors in electric vehicle is AC. So again you have to convert from DC to AC. Air conditioning unit inside the car, again you need AC, and then all of these small power 14-volt power outlet like your light and other appliances, again you have to convert that into 14-volt level. So this is the importance of power electronics in an electric vehicle. So this part where you have a battery and to convert and move the electric vehicle, this part is called propulsion unit. So what I'm going to take it is I'm going to concentrate on this propulsion unit to address this EMI issues. What is EMI, and how you can measure and how you can mitigate some of the methods I'm going to discuss further. Okay, so as the name suggests, EMI is electromagnetic interference. How electric and magnetic fields in the system degrades its own performance as well as the nearby nearby system performance. This is what electromagnetic interference. There are two types of electromagnetic interference. One is conducted mode EMI. So what is conduction? So as the name suggests, it conducts, the current goes through the conduction and it is unwanted. Automatically it gives some other effects. Say for example, in this figure, there is a source, there is an inductive coupling, and this is say parasitics. This capacitive current affects the victim. And next one is radiated EMI. So this is our proximity effects. Any current carrying conductor will interact with the nearby current carrying conductor because these magnetic fields can interact. So this happens at very high frequency in a larger level. So you can say the source will transmit, act like antenna and then receiver. So source will transmit in radiative nature, like how you are receiving energy in the normal way in the telecommunications and other Wi-Fi, this thing. So this is unwanted energy. So this will go and affect your victim's operation. How it does, we will see in due course. So in general, for a power processing system, main EMI sources switching and inherent parasitics which exist in the system. Okay. So in power processing system, more widely researched is conducted EMI until now. The radiated EMI is overlooked, and the only solution which has been offered until now is shielding. This to provide a proper shielding, metal shielding, so that the conductor doesn't interact from one to the other. Whereas for a conducted EMI in a power system at higher power level, it's very difficult to deal with it because of its uniqueness. It's very, you can say it is system dependent. You cannot give a unique solution commonly. Okay. So now if you look at the EV, the noise sources, where I had been telling individually, there are batteries, there are converters, there are motors. Motors are also load, so that will also get affected. And the converters and sources will act as the sources for EMI. And who is other victims apart from its own system? Who will be the other victim is, if you look at the car has lots of small power electronics and sensing units. So it has to process some information. Say like you have a sensors for sensing some information, LED brake light. There are many options, so they have given. So all of them will operate at some voltage level. If this interact through the ground current or the common mode current or the conducted EMI, or if it affects through the radiation, its function can malfunction. Say in automotive vehicle, for example, you try to brake it. What if opposite happens? So it's a very worse situation, correct? So there is that much problem is there if we are not addressing it properly. So we have to be careful in automotive applications. This standards has to be very strict, and it has to be tested several times before it goes in the market. So the source is the power converters and the switches, and the victims are all other electronics which are present in the system. Okay, so now we have seen how it in overall electric vehicle, the EMI can lead to a problem. Next, I'm going to go into only the propulsion unit, and in propulsion unit, how we will further define what other problem is there, how we can reduce it. So I'm going to go into little deeper from now onwards. So what is variable frequency drives and its adverse effect? So we are going to see only conduction mode EMI from now onwards, because it's been more, affecting the electric vehicle or the normal power electronic system more than the radiative effects until now. So we will see more about that. So what is variable frequency drive? Let's say here. So the first figure, which I'm showing it here in the cursor, this is your basic structure of variable frequency drive. What it basically does is, drives is basically controlling the motor. We are going to control the motor by changing appropriately the electrical input. See, for example, in a car, what we would expect, the motor, the motor which is fixed for wheel controlling should act as per our modes of car's operation. Say, for example, at the time of starting, the car, from motor, what it is required is, you need lots of torque to pull the entire weight of the vehicle, and the speed would be at the time of starting, it would be 0. And say if you are going on a highway, the speed requirement would be high and torque requirement will relatively go down, and so on. So based on the modes, this motor has to change its speed and torque. Now, how do we do it? This motor has two ports. Input port is the electrical terminal. Output port is your mechanical terminal, where the other loads are connected, like wheel and other things. So now what I have to do is, I have to change the electrical parameters such a way that the speed and torque has to be changed. So for each motors, this method, how to control the speed and torque would be different. Say for this example, we have to take the speed torque characteristics of the motor and the load, and then we have to find out how to change the speed torque characteristics by changing the input voltage and frequency. Who is going to do this? These converters will do this. Converters will change here from a fixed AC source and fixed frequency to variable voltage and variable frequency so that it can control and the speed and torque of the motor. So this is the general basic, very basic structure. In electric vehicle, direct torque control scheme is very widely used. That is employing the closed loop and just dealing with the uh, basic structure. Okay, what are all the adverse effects? The benefits of this is, say in industrial applications, you can save lots and lots of energy. Almost 40% of energy produced is more used for industrial processing, and now it's started even for electric vehicle and others. So automatically then we have to save energy so much that we can save other energy depleting energy sources and so on. So VFDs has changed the entire industrial this thing in terms of efficient way. In fact, one of the reason why vehicles has to adopt the electrical vehicle is main reason is the one is of course the pollution, other is efficiency. If you receive a mechanical system, the efficiency will be of 20 to 30% max. But if you see any electrical system, definitely 80% and above is guaranteed. If you are operating at higher load, automatically it will result in better benefits also. So there are benefits. There are many proved benefits. So what is the adverse effects? If we say the adverse effects would be, we are see the processing power required at very low frequency. Say for example, the motor, we have a 50 hertz. So correspondingly, it is the processing of motor also requires only 50 hertz. But to achieve this high efficiency, we are using the switches. In turn, we are producing some form of square waveform. Correct? So that will have a n number of frequency component, just not the fundamental F50 hertz. It will have a multiple number of frequency component in different magnitude. Okay, so that would introduce two different paths, namely common mode and differential mode. We will define what is it, and electromagnetic interference. In motor, it will also produce something called shaft voltage and bearing currents. And this will, overall, what would be the effect of this? One is reliability and another one is safe operation. So this reliability will give a lots of loss, you could say, in terms of downtime cost. If in industries where it has to run fully, even if something failed and even if it is cut off for 50 minutes or half an hour also, it's a huge downtime cost would be involved. And reliability, of course, we know one product we buy and use it for just 1-2 days. If it lost, we will know the pain, correct? So the same thing. So we have to look at reliability aspects very carefully as the product manufacturer, and then we would see what is this definition, what is each of the adverse effects we will see now. So the first adverse effect, the common mode and differential mode, this is part of the conducted electromagnetic interference. The conducted electromagnetic interference is defined as the common mode and differential mode. So take two wires. So this is the two-wire system, and here I have shown three-wire system. So if you take a two-wire, it is easy to understand. So there is a load between two wires, the load is connected. If there has to be a current between the wire, who will be the source for it? The voltage difference between these two wires, that is V1 minus V2. If so, we have a common grounding. Say in your home, everywhere, the grounding is very, very important. Why? Because whatever we touch should not affect us. So any product you touch in your electrical appliances would be grounded on a frame. The frame has to be grounded, need not be the inside material, but outer frame has to be grounded for your safety reason. So ground is, very important. You cannot avoid this ground. So the ground, if you have if you have a common ground, each wire will form a parasitic capacitance. So what is this parasitic capacitance? Why is it necessary to be present in the system? We'll see. Okay, it would be automatically formed whether you like it or not. So because if you see what is capacitor, two conductors are separated by the insulating medium, correct? Okay, so and this capacitor presence would be realized if you have a voltage change across these two terminals. In any electrical system, if you take it, there are different parts would be operating at different potential unknowingly, because there are drops somewhere, there are add-on values, so automatically the wires will have some inductance, and then at different points the voltages will be different. So between these 2 points, say for example the top wire and the ground, the voltage will be different. Between this V1 and V2, the voltage would be different. So automatically, even if the wires are insulated and placed nearby, the parasitic capacitance will be present. And when this will be more visible is if your switching frequency is higher. Why? The capacitive reactance Xc is inversely proportional to frequency. If the frequency increases, the capacitive impedance will become lower and lower, so it attracts more currents towards that. So the parasitics at higher frequency will inevitably affect the system. So if you look at back to the definition, so between the wires, the current can flow only because of the differences between V1 and V2, and from each wire to the ground, this can flow because of each voltages V1 and V2. And if you collectively look at who is giving the ground current is the average of these two. If you assume the capacitances are equal by symmetry, the VCM, common mode voltage, is V1 plus V2 divided by 2. This is for two-wire system. If you take it for a three-wire system, the same thing you have to extend here. Each wire will connected by the capacitances to the ground, and between the wires also you will have some capacitances. Who will allow the current between the lines is called the differential mode noise. Who will allow this unwanted currents through the ground is called the common mode noise. And source of these voltages are, say, the same way if we extend, addition of all three, this voltage VAO, VBO, VCO is common mode voltage. And differential mode voltage is the line to line voltage. So you could see this is the definition of common mode and differential mode. Basically what is this is, you have some source, the paths are different, so automatically they will give a different effects in this system. If you see in the drive system, drive is like your propulsion unit of the electrical vehicle. The source, these currents will start from the source and circulate between the lines in the that is called your differential mode current, and come to the ground through the parasitics, again come back to the source and circulate it. That is called your common mode current. Both common mode and differential mode currents will contribute to the electromagnetic interference, but this common mode currents will pollute commonly the ground. So it would affect its own system, and all other, say in our house, everything will be connected to a common ground. So automatically, every possible ground currents will circulate through all the systems, so it would invariably affect everything. Right? Yes. So differential mode, more of, you could say it would give a problem in terms of radiation, because it doesn't conduct or pollute from one point to the other except flowing between the lines. It would cause some problems to the motor, of course. It will create an insulation failure. Reason is this voltage at this point will be reflected at higher level here, and it would there is a damaging factor for the insulation of the wire. And common mode voltage will introduce the electromagnetic interference, shaft voltage, and bearing currents. we will see what is shaft voltage and bearing currents. What is shaft voltage and bearing currents is, so it is little, a very unheard topic for even for the electrical engineers. So I will just give the brief of it, not going in depth. So this is the electrical equivalent circuit of the motor. So you have a stator winding and you have a rotor winding. The neutral points will have, this is the lumped parameter equivalent capacitor circuit. How it is coming is, this is your motor structure. These capacitances would be distributed in nature. As I mentioned here, it's not going to be looking like a lumped way, but it will be distributed in nature. For our easy understanding, it has been put here in a lumped form. So if you see it here, this is the windings. We are placing each winding in the motor, and then it will we will be winding for n number of turns to meet our inductances and so on. So from winding to frame, frame is nothing but your outer cover. There would be capacitances formed, and winding to rotor there will be capacitances formed, and again rotor to frame there will be parasitic capacitance. Automatically it will form, and every if you look at it, frame will be a different potential, winding will be a different potential, rotor at different potential. So these potential differences will activate these capacitances more. Apart from that, our motor is fed from the inverter, so high frequency noises also will come in, so this will give a lots of currents, or you could say the parasitic capacitive paths. The depends on your grounding, this will be higher. Okay, so now if you look at it, this capacitor CRF, across this your bearing would be there. This bearing you can model it something like this, like a nonlinear switch with the insulation. So whenever this voltage exceeds the lubrication breakdown of the bearing, it will see a current called electric discharge machining current. It is like our capacitive current suddenly discharged at one moment, just an impulsive moment, it will discharge. This will lead to a kind of the flooding. This, if I'm showing this figure 19 below, this flooding in the metal of the bearing. This is like, damage in the metal of this thing. So what will happen is this flooding will eventually increase the vibration of the system and will introduce lots of asymmetry in the system. So eventually will lead to permanent failure of the bearing. If you remember, the purpose of the bearing in the motor, it just separates your stator and rotor. The entire weight is placed on this bearing, right? It separates it. So if bearing failed, then it will lead to shutting down of the motor completely. So this more widely researched on the mechanical aspects, even the electrical drives is giving a problem to the life of the bearing. Okay, so now we have seen overall in a drive or the electric vehicle propulsion system, what is the benefit and what would be the adverse effects? How does it affect? So the overall, the EMI will give a control disturbance to its own system and its nearby system. Fault tripping. So what is fault tripping is, I'm just giving an example. In your inverters or any system, first there will be a sensing. Many places there will be protection required, or many places based on some sensing you will take the action. Say if my voltage reached this much, say in the smaller power level, say in larger power level, 600 volt and above, you don't want to run the system. Then you will sense it in the sensor, getting down that value in terms of 10 volt. If this 10 volt here, if it reaches, in my main power circuit, 600 volt reached. Then what would I do? If it goes above 10 volt, I have to cut down. So this sensor has to sense this information. If there is a noise above it, much before this 10 volt would have not reached in the system. What would happen? This noise will present on top of it and give a false information. This will lead to false tripping. The problem of false tripping is you will not know what is the reason. You have to analyze. Is it really a problem occurred, or is it just the fault tripping? If you are, overlooking at it, If you just adjust the value, if real problem have occurred, you will eventually lose some of the part of your system. So fault tripping is, one of the major problem of electromagnetic interference. And another one is insulation failure. Like I said, the differential mode voltage introduce the peak overshoot of the voltage. The voltage, say, if you give at, you can say you are intended to give 415 volt, but at the motor terminal, it will reflect even more than half if your cable size is more. If your converter is placed one end, and if your motor is placed in the other very larger distance, the cable will reflect its voltage at higher level. Eventually, will spoil the insulation of the motor. Okay, so these are all the issues because of the conducted EMI or common mode voltage or differential mode voltage in the drives. What are all the general solutions given in the literature? If you look at the system, there is, in a big picture, if you look at it, there is a source, EMI source, and someone is allowing it, which is propagation path, and one is a victim, which is your load. Okay, so you can try to reduce one by one. Say first, I can take my EMI source. I can try whether is it possible to reduce the noise from source side. Still, I will be able to achieve some comparatively some performance in the motor. See, ultimately, your aim has to make your motor run. Without that, without disturbing more that, you have to try to reduce the source reduction. There is a way by changing control and PWM techniques. I would explain some more later. And then you increase the propagation path. See, the now propagation path is easily allowing the noises. If the path is little bit resistive I mean, is it's not allowing the these unnecessary component, then the load or victim will not receive it. That is design change, alter. You look at your entire system, how to reduce this ground current, how best I can make my layout of each of the component so that the EMI seen by the system is very less. And another is passive and active filter. Okay, victim we are seeing as a load or some part of the system. Instead, I make someone voluntarily as a victim instead of something else. Say like I'm going to place a passive or active filter who is going to absorb all of these component and give pure component to the motor. That is what your passive or active filter. If you look at overall solutions provided in the literature, this is the summary of the literature. There are n ways and methods, how to reduce some solutions, how effective, how can I simplify the solution and so on. So overall, these are all the solutions you can give it for EMI reduction. So this is summarized here for the propulsion system, figure 17. You can look at it. See, there is an inverter. I can control this inverter because I am going to use the controller to control the electrical input. So there will be 3 output voltage will be seen here. And these 3 output voltages, I can change their frequency profile such a way some of the components are reduced by control algorithms and PWM techniques. I can take the feedback control. And if you notice it carefully, this common mode voltage is also called zero sequence voltage for this system, star and delta connected system. So what is zero sequence voltage? You could have studied in the symmetrical component theory. So you can use that as also input, control input. Until now, we could have done more of, VD, VQ control, and you include zero sequence control also. That is the other option. You can control the zero sequence voltage. In turn, it will have a lesser impact in the load. And another thing is, as I said, you place wherever, whom you want to protect. You want to protect from here, you insert a filter here. You want to meet some grid standards, you put a filter here. You want to protect the load, I have put here in the perspective of load. So here, if I put here filters, automatically this all of the unwanted components will be absorbed by this, and then the rest of the components be allowed to the motor. This is for, what are all the methods in general suggested for the bearing. So if the insulation is there in the bearing, it will stop the conduction between the stator and rotor and reduce rotor coupling. So these are all the some of the methods for reducing the particular shaft voltage and bearing currents alone. Only that, how can I protect the motor from bearing problems? That can be solved by this. Okay. So this bearing current problem will be more problematic in some of the appliances where say in paper mills the shaft is coupled with lots of motors. Not one motor will do the work. Lots of motors are coupled on a common shaft. So in these cases the currents will be circulating in a different places in a different manner, and someone who is having low impedance will get more severely affected. So it depends on your application. You have to check it whether this is really a problem or it can be ignored. And if you look at in real time, the manufacturers will make sure the converters which has been produced is meeting the standards. Like they will make it such a way that the EMI emission, or you could say the conduction, everything is very less seen from the product itself, because otherwise they cannot sell the product. If we use it for some house appliances, it has to meet some of the standards. Okay. Yeah. So these are all the introduction to the common mode or differential mode noises in the drive system. Okay, so what is the motivation? Why do we have to affect? I have told you what is the effect already in the system. First, if you are a product manufacturer, you have to meet the international national standards, otherwise your product will not be approved. So first you should know how to lay out, how to reduce your it starts from the converter. If suppose if you are looking at a converter alone, what you have to look for it is you have to try to reduce the parasitic inductances. Say for example, what I mean parasitic inductances is you are connecting the converter in some form, and between each element there is a wire connected. If you use a solid wire, the inductance would be different. If you use some metallic platform with the surface area or a different method, the parasitic inductances can be reduced. So you can try to lay out properly. The parasitic inductance is less. In effect, this will reduce the parasitic capacitive currents. Why? See, you have a switch. Inductance matters because whenever there is a switching action happens, the inductor have a nature of opposing the sudden change in current. So whenever you open or close the switch, so first you close the switch, inductor will store the energy. When you try to open it, even that parasitic inductance that will try to impose and produce the high voltage across the switch. That is what your peak overshoot, right? So if peak overshoot is increased, automatically your current through the capacitances will increase. So if you look at the converter alone, you have to meet the reduction of parasitic inductances, and you have to reduce the parasitic capacitive paths by laying out the proper grounding inside the product. This is when you manufacture. And if you are going to make some system, overall system, see what I will do, I'll buy a converter, and then I'll buy a motor, and then I'll check what source I have. I'll try to formulate a system for a different particular application. Say in my house, a product manufacturer will come and install it, correct? Okay. So unknowingly, if we place a long cable, automatically the EMI, whatever met the standard, will not applicable in the overall system. It will create a different EMI in your system. So if you want to increase the reliability of the overall application, you have to look at again the layout, how to reduce. Am I meeting the standard? Should I place some filter this side? Or my load is very important to protect from these noises. Is it sensitive? Should I protect it? These aspects you have to see. Okay. So in electric vehicle, we look at this in two perspectives. One is for a safe operation. Yes, this is very important, correct? You don't want to get into an accidental modes of operation, correct? Another thing is reliability improvement. You buy an electric vehicle, you don't want to leave it in a, for a frequent repair and this thing, maintenance, correct? So reliability has to be important. For these two reasons, we have to address EMI in electric vehicle. Okay. What is the research scopes? What is happening in as of now in this particular field? So people had been working on, EMI in this, you could say, the high frequency effect for a longer time. But what are all the other EMI noises sources? They like mechanical sources. So low frequency EMI standards are still evolving. People are still looking at what would be the effect in the real life, and so on. And other thing is to reduce the size and weight of EMI filter solution. Look at the drive system, the propulsion unit, more than 30% or 40% of weight is for EMI filter. Any system, if you take it, you insert a filter, it would introduce a larger size and weight. One of the reason that, electronics hate to use the inductor is this. Now, of course, there are many evaluations and everything, but the size and weight has to be reduced. This is one of the research scope which is happening. And the as I said before, common mode parts are, and its solutions are system dependent. So it's unique. You have to address it each time. You have to find out the layout, sources, what is that, how can I reduce it for my system, and so on. And hybrid vehicles. So now, say one source alone cannot run for a longer time, and say like battery alone, we cannot depend on. Now fuel cells are coming, some other sources. People are trying to use it. So if many sources, if you are using, how that's going to affect your EMI? Okay. So now I have defined, overall in a layman term, what is EMI. And now we will see how to measure it in actually, how to measure it. So all vehicles has to be verified for EMI. There are IEC standards, there are CISPR standards, SAE J551, and there are so many other standards you have to meet if you are making a product for both conducted and radiated modes of emission. Okay. This is your overall drive system. I have a battery, I have an inverter, I have a I have a motor, and I have a cable. Fine. And we have to use something called line impedance stabilization network, which is LISIN. What this LISIN does is it it helps us to measure the noise of its own system. It won't allow any noise coming from the source side, and it will make sure the noise is measured only from your own system. The effect of line impedance will not be there for your system. Say you have a grid impedance, you have other line impedances which affects the measurement if you are not using this. The main purpose of line impedance stabilization network is you measure what is actually emitted by the particular system. Okay, so these capacitances here, these capacitances value will be generally much higher than this, so that the entire current coming towards the ground will go through this Vx and Vy only. And similarly, this won't allow, these inductance won't allow any of this current goes this way as well as from here to come. So this is like a filter basically. I will make sure how only system measured noises are measured across these two. So this is Vx. So generally Vx and Vy is measured, or only Vx is measured for common mode, or we will see in due course what is the definitions in terms of equation, how to make it. Okay. So this is your this thing. So as I said, common mode component is the one which is common for all three phases, correct? It is common for all three phases. So what we can do is, see if you are, this is for a three-phase system, and here this is if you are doing it at LASIN terminal, you have to use Vx and Vy for measurement of common mode and differential mode component. If you are using IA, IB, IC, the current probes generally you can clamp across in a one direction. This dot terminal shows clamping the current probe in a one direction so that the common mode currents can be measured in the across these three phase lines. The same thing you can do it here also. If you have a current probe, you can clamp across these two lines. So that would measure only the common mode component. Okay. So what is the differential mode component? How do we do it? So first we will see the equation and then we will come for this measurement again. So DC side CM. So if you look at the DC side is this, AC side is this. If you look at DC side, I have said all of the noises will be made available across Vx and Vy. As I have defined for a two-wire system, what is common mode? It is Vx plus Vy by 2. If you want the current, you divide by 50 because this resistance's value will be 50. 50 ohm resistance would be there by standard. They have already, calibrated and found, which value of resistances and capacitances would be sufficient for all overall systems. So ICM is Ix plus Iy by 2, which is same as your definition of your common mode voltage for a two-wire system. And IDM is Ix minus Iy. Once I measure Vx and Vy or Ix and Iy, I say the difference of this will give my differential mode noise. The addition or average of this will give my common mode noise. So this is measuring at DC side. And then next is next is at AC side. AC side measurement, see, there are current IA, IB, IC is flowing. There is only two components are available, correct? One is common mode. It is going to go in two paths. One is the common mode path. Another one is differential mode path. We are able to measure the common mode path. So what I can do, I can subtract from the overall current and find out what is my differential mode. That is what your differential mode. How it is done? ICM is IA plus IB plus IC divided by 3. And I can define as the DM component for A phases. I measure this overall current and I measure the common mode component. So IA minus ICM by 3 will give me ICM by 3 actually. ICM by 3 will give me the, I think here the equation is wrong, 2IA minus IB minus IC by 3. Rest of the equations are correct. You just have to subtract from overall A phase component to the per phase common mode component, then I will get my DM component. So this way, I can either measure on AC side or I can measure on DC side based on your interest. Where do you want to measure? This is, conduction mode and conduction mode EMI measurement. In general, people would like to address both of them together, conduction mode and differential, common mode and differential mode together. That is called conduction mode EMI filter. In general, for any propulsion unit, it is called, EMI filters or EMI mitigation methods. So we measure both. There is no, prediction in differential mode. It is easy, which noise is dominating and so on. But in common mode, it is difficult because it is system dependent. So what generally people do is, I measure common mode component of my own system. I measure differential mode component of my own system. And then I set my bar of, how much attenuation required. And then which method I would adopt for my system to mitigate and meet the standards. If you are looking for meeting the standard, you have to look for how to meet the standards further. Okay. So until now, we have seen, the introduction, and then we had gone to measurement method. So one of the method I have told, there are methods to control through PWM methods. Yes? Yeah. So though it's those who have not studied power electronics, this slide would look very different. Until now, I think all electrical engineering, at least they can understand. This is a method, the space vector method is one of the method to control the motor through inverter, space vector PWM. So here, this 1, 2, 3, 4, 5, 6 is called active vectors because this would result in a power flow between a DC side to AC side, these switching states. And 7 and 8 will result in, it's a zero vector. This is called zero vector. It won't help in power processing, power flow from source to the load. But how does it help is, it will reduce it will help to adjust the length of this vector. So we look at these 8 states only we will use it to realize our sinusoidal source using the converter. We know we are using the switches, and that will not result in actual sine wave at the output. You will get only the square waveform, some square waveform. So automatically it is not going to result in a pure sine wave. You can realize in average way. Average in the sense, averagely you could see some sine wave at the end output. Correct? Yeah. So if you look at the common mode voltage of all these states, each states, if you look at the active vectors have plus or minus VDC by 6. What is this common mode voltage? Average of all three input voltage, whatever I have defined, VAO plus VBO plus VCO divided by 3. And I get plus or minus VDC by 6 for all of the active vector states. And if you look at it, this zero vector, which I am using it to control the output voltage of the inverter, is giving a highest common mode voltage. It is plus VDC by 2 and minus VDC by 2. If I can avoid these two states somehow, I would be able to limit the common mode voltage of my system to plus or minus. Yes. So how do I do it? Is the main purpose is to adjust the length of the space vector. I can try to do it by using in the zero vector period, use equal and opposite vectors. Say instead V7, V8, I can use V3 and V6, V1 and V4, V2 and V5 as the zero vector, because zero vectors are used just to adjust the output voltage. Okay. So this is called active zero vector PWM. There are n number of ways how can you reduce the common mode voltage using the space vector concept. And the same thing is there for using carrier based PWMs also. So the effects is seen here. So if some PWMs, SVPWM is resulting in the FS and multiples like this, and AZ PWM can reduce overall at the switching frequency multiples. It is clear also, correct? The PWMs cannot have a control at higher switching frequency, because the higher switching frequencies are what? Our rise and fall time components. Rise and fall time components cannot be controlled by PWM methods. What you can control is where the PWMs have an effect. Where you can change the PWM effects only at the switching frequency multiples, FS and its side harmonics. This is what we have a control. So the PWMs, if you use as a solution to address, it can reduce the switching frequency multiples. And using this, what we have done is we have reduced the filter size. Filter size in the sense the attenuation requirement at switching frequency multiples would be different for SVPWM and would be different for AZPWM. So either you can reduce the attenuation stages required, filter stages required, or you can change the cutoff frequency and further reduce the size of the component. This is what the benefit. We have done work on this as the first work for the EMI mitigation filter solution, size reduction. And this figure has been, this is using the LISIN and the EMI conduction mode EMI spectrum analyzer we have. We have measured for our SIC inverter. The switching frequency is at 50K. And there is a jump here because the standards used below 150K is different. The standards above 150K is different. So 150K to 30 megahertz, you have to use the different. So that is why there is a jump seen here. Our switching frequency starts here. Okay. So this is how the EMI spectrum. This is the common mode EMI spectrum. This is common mode, differential mode I have missed. Almost that will also look similar based on your system design. Some places, mostly common mode will dominate than the differential mode. Some places differential mode will dominate at higher frequencies. Okay. Then next is the EMI filter. I had put only the EMI filter as the solution because, in fact, even filter people will not prefer in the industries. People will mostly prefer what I have put it here, common mode choke. Common mode choke or a choke. People would like to put either a choke or a filter because of its easy adaptation to the system. You don't have to design, very huge. You don't have to look at what is your system and so on. I can just employ this and try to meet my standard. This is the very simplest way. And the practical systems doesn't go for this active methods and some other very complicated methods which has been produced in the literature. So that is why I have chosen only EMI filter. So it's simple as we had been doing it from the normal filter design. You have to choose the cutoff frequency and choose L and C values, right? Okay. So decide the attenuation required for both DM and CM filter at FS. So this is for EMI output filter. Output filter is nothing but this place filter. This design I'm going to talk for EMI output filter. There are different goals you can have it. Either you can have the output of this filter as a pure sine wave, such a way that it would see a pure AC to AC conversion here, the load, or you could see only the noises can be minimized. You can keep the goal. If you want to have a sine wave at the end, you have to make sure all of the switching multiples is reduced. So then you decide the attenuation at Fs and choose the F cutoff for both differential mode and common mode. So it has to be the F cutoff has to be greater than fundamental component, that is 50 hertz, and then much less than your switching frequency, because you would like to attenuate from 50 hertz to the switching frequency to further high frequency component. Once you do it, first design your LDM. How do I design your LDM? I have decided F cutoff for my differential mode filter, and I have to design my LDM such a way that how much ripple has to be allowed to the line, because the inductor will decide how much is the ripple in the current. How should I do it? Simply apply VL is equal to L into di by dt and find out, decide how much is del I you want to apply. You want to have it in the output of the three phase, and then you choose your LDM accordingly. Once you choose LDM, your CDM can be found from F cutoff because you have done it already. To avoid the oscillations, the resonance, you have to add the RDM based on the Q factor, which is nominally, it 0.707 for a system, and depends on the system, you define what is RDM. And then next thing in the LCM filter. So this is for DM filter. Since the paths are different, both DM and CM filter has to be employed to remove overall EMI. So what is first condition we have to do when I employ is the LCM has to attenuate a huge number of component, because it should see capacitor will just bypass it, right? So you have to, and some impedance would be there, but higher frequency, the impedance offered by this will be lower. And if you look at inductances, impedances offered by the inductances will be higher for higher frequency. So this condition first has to be met. XLCECM, LCM has to be much greater than XCCM. The common mode capacitance X has to be higher than XLCM, at least a particular designed frequency range you want an attenuation. Therefore, LCM has to be greater than CCM, and CCM, this motor capacitance, has to be much greater than what is the motor parasitic capacitance or the load parasitic capacitance, because the current will be bypassed from here if this capacitance is higher, or if this impedance offered by this filter has to be higher than the load, so that all the current would be bypassed here. These are all the basic rules. What is this? Why there are two types of chokes has to be used. One is the normal inductor, Another is, what is this common mode choke? Let's see what is it. Why we have to put a common mode choke and differential mode choke separately. If you look at the first figure here, common mode current will flow both in the same direction. For a same direction of current, the flux will be in the same direction as seen in this figure. So you can see the arrow. The flux would be in the same direction. So it would see the maximal impedance. The L, total L will be seen by the common mode component if you use the dot polarity here like this for a common mode choke. And differential mode component, what is differential mode component? The direction of currents would be different. So the current flows forward and current flows reverse. So these two will oppose each other and gets cancelled. So the common mode choke will cancel the differential mode component here, nullified. So the entire differential mode component will be passed to the motor unaffectedly. So you want a differential mode component at the motor, so the choke will attenuate only the common mode component, except for the leakage inductance of the choke. So most preferred method by anyone is inserting a common mode choke for a common mode problem. And if you have a lots of differential mode things, mostly this would be taken care by the designs. If you have still further, people would like to go for the EMI filter. Any of your SMPS applications, switch to mode power supply applications, will have a front end filters inserted already. People would have done in the product overall. They have already inserted these filters in your as a front stage or the back stage based on the grid requirement or the load requirement. Yes, so this is the output of the EMI filter which we have tested. So this is my common mode current. The common mode current is almost nullified here. This is in terms of frequency spectrum. You could see none of the frequencies are present at FS multiples. And you could see the voltage and currents both are almost near sinusoidal because I have used EMI sine wave output filter, and there is no sharp voltage, there is no common mode voltage. Of course, I have not put here without filter what is this. So it has eliminated considerably. These two will be considerably higher without filter. And here, this will be some form of square instead of sine, the output. Okay. So overall, the two methods we have discussed. And I would like to wind up. Sir, how much time more? 5 more minutes?
Yes, madam. Yes, madam. Already, okay, uh, we are running short of
11
time.
now.
Not a problem. Of course, we have a couple of questions to answer.
Mhm.
You can take time, ma'am. Another 5 minutes you can take if you have any stuff to share.
Yeah. Okay. So this is just those who are working in the field in the research. Those who are doing. Now previously the silicon based technology is more used in the converters or inverters. Now the trend is moving towards silicon to silicon carbide. What is the benefit is this is called wide bandwidth materials. So this reduces, you could say it increases the switching frequency further. See, there is a limitation in increasing in the switching frequency uh, because of the losses. Generally, we don't go for higher and higher switching frequency. The main reason is the losses. But these devices are able to rise and fall at faster rate, is able to switch at faster rate, so you can improve the efficiency. So can you switch off the
Uh,
mic somewhere is disturbing.
okay, I'll check. I'll check.
Yeah, yeah. So this leads to increased bandwidth requirement of the attenuation. So now SIC inverters, straightforward, we can go for low power applications. Low power I mean 400 volt and up to 10 ampere even 10 to 15 ampere. You can go with the 50 kilohertz and 100 kilohertz and above. The efficiency will still meet because the rise and fall time is very high. It can rise in nanoseconds. That is the biggest problems of the electrical switch. You have to rise at faster rate. You have to rise at fall at faster rate so that it doesn't occupy the most of the efficient time period. And the main concern until now to go at high switching frequency is losses. So since that was met, now SIC converters are more popularly being adopted, or technologies being developed by many companies. Almost technology is getting matured, but still literature is going on the EMI filter size reduction and bandwidth requirements. How to reduce how the bandwidth has increased. See, previously, the rise and fall time will be like few megahertz, like 800 kilohertz to megahertz. Now it has gone up to megahertz, 1000 megahertz until then. So now people are working on, okay, now I have to move further, and then I have to increase the bandwidth of the attenuation methods. The magnetic materials at high frequencies are really, really bad. Really, really bad. If you have anyone have made a common mode choke, you can look at the impedance profile. If you could see, it would become inductor to capacitor for a particular material. You have to carefully choose the material also. It is not going above 1 megahertz. This is you try at any level, the chokes are really bad. So one way is you find an alternate solution for a choke, which is not feasible. People are working on a material side to improve the magnetic performance of the chokes. There is a belief if you increase, and it is true also, we had been doing until now research like that. So there is if you keep increasing the switching frequency, your size of the magnetics would go down. There is a problem when you go at higher and higher level of frequency. The inductance for the actual choke, with the increase in frequency, the inductance will keep changing. Mostly it will degrade. Say at if you have to make a real life inductor, you have to see at what frequency you have to how much inductance you have to have. See, if I design at 50 kilohertz, say my inductance is 1 millihenry. If I look at 1 megahertz or 10 megahertz or 50 megahertz, the inductance would have almost fall down, and some places it will act as the capacitance. So then you have to see how do I attenuate larger range of frequencies. And for doing so, suppose if I want to meet at 1 megahertz some inductance, okay, we have been telling, okay, if I increase the inductance, if I increase the switching frequency, my inductance requirement is less, thinking that my inductance is constant over the frequency. No, it is not in real case. So say if I made a choke at 20 kilohertz, if I make a choke at 100 kilohertz, 20 kilohertz to 100 kilohertz for the same choke, the inductance would have been already reduced. To meet the same inductance, which happens to be which happens to happen in common mode, this thing, if you increase the switching frequency, the common mode component will move, but the required attenuation remains same. It won't change, it won't reduce it. So then to meet the same inductance, you have to increase the number of turns. So if I need it here 1 millihenry and 50 kilohertz, I need 1 millihenry, I have to make so many turns increase. So this has increased the size of a choke instead of decreasing size. So this is one of the problems to be addressed. It's still people are working on. We have not yet achieved any solution. Bandwidth improvement, people are trying a number of combinations, like some different filters, trying at one attenuate for some frequency range and other attenuate for other frequency range, so that overall frequency attenuation bandwidth has been met. And EMI radiation aspect has been less research in power electronics because we believe that it's not going to affect us more. But with this SIC inverter, the range of frequencies are different. Very few literatures has been worked on how to change the shielding methods for power systems. I mean power processing system. And another problem is replicating the technologies from low power to high power. Say, for example, we have been working on negative impedance. What is this negative impedance focus? So negative inductor, the negative capacitance. Is it possible to make it? You look at more about the electronics side of this. If you have a op amps, you can add some auxiliary winding to the common mode choke, and you can improve the gain of the choke more at a particular frequency range. You can change the gains of the attenuation. So that has been done at a lower power level because op amps are available at lower power. So we had tried to do the same thing at higher power level with the passive components available. So the result is not so much, fruitful, but still we are working on it. How to, replicate this gain change and still, for the inductance reduction for at higher frequency, how do we address it? We are working on it with this extension from a low power to a higher power, how to do it. And then we have been also working on the mixed mode noises, how conduction mode noise will have an impact in the measurement on the CM noise will have an impact on the DM noise measurement, and how DM noise will have an impact on the CM noise, because based on the measurement only we decide the attenuation requirement. So these are all the things which is happening in, you could say, in the propulsion unit of EMI mitigation methods. Yes, that's it. Thank you.
Thank you so much, Professor. It was a really wonderful session, and I hope everyone would have got some ideas. And the challenges that you have posted, definitely that will help new researchers going to come up. It was really covering all the topics which is essential or inevitable to the electric vehicle. I really thank for this, and thank you for spending time and putting your efforts. Thank you so much once again. And I'm thanking
Thank you, sir.
participants also. Thank you, madam. I'm thanking all the participants for the patient listening. Madam, we have some questions here in my chat box. I can share with you. If time allows, we can
Yeah, please. Go ahead.
answer for that. And of course, you can check
Yeah.
your chat box also if there are any questions posted. Meanwhile, I'll read out one by one.
Mhm.
There is one question. I would like to know what all major parameters which can be calibrated in an EV ECU for efficient drivability and optimized battery usage. So I can.
Okay, that is actually that is entirely the different topic, control unit. What is the question? Can you repeat? It is basically, I think, battery management system. Based on
Yeah,
battery management system.
I would.
Yeah. Can
I'm repeating it. I would like to know what all major parameters which can be calibrated in an EV ECU. Yeah, as you said, it is more of controlling part for efficient
Yeah, yeah.
for efficient
So
drivability and optimized battery usage. Yes.
yeah. It is basically a battery management system which has to be, combined based on the modes of operation, how to, incorporate, regenerative braking and other things. As of now, I'm not working on, electronic control unit of the vehicle. Soon we will be taking it up. So I'm not worked on that topic.
Okay, madam. I'll read the other question. Is there some known impacts that the EMI due to electric vehicle charger is causing on the grid where it is connected? That is, from where the charger is being fed from. Can you elaborate on
Yeah.
some practical issues that are being seen in the grid?
See, charging stations, definitely it will have an impact based on your system. Say, for example, ground is common. Your charging system, ground is common. Even if the ground is not common, it will formulate parasitic capacitances. So if there are electronics present in between, say in the charging stations, hopefully we are not going to do it in the home, so it won't affect it. So we will be doing it in the charging stations. Each charging station will take care of it, isolating one from the other. Try to avoid so many, you know, uh, you could say, the charging stations will definitely will take care of it. We will not do it in the home for the higher power application in the future when we are going to adopt the this thing. If you are going to do it in home, definitely it will have a huger impact, because we are going to connect all of the grounds in one place, and again this battery charging and everything would be connected. The effect is like, as we said, It would be the currents in general. If I say what I have measured is like 1 ampere peak maximum common mode current in the drive. Depends on the currents and what is the sensitivity of the equipment. Sometimes the sensitivity, the equipment can go or equipment can malfunction. It is something similar to if you allow a larger neutral current, you know if you allow a larger neutral current, what are all the effects you would see, it would have the same impact.
Okay. Ma'am, there is another question from PhD student from Arizona State University.
Mhm.
Doing PhD from Arizona State University, and my research is on powertrains for EVs. I
Okay.
have 10 kilowatt hardware setup where I am using RL load to model
10 kilowatt, huh? 10
10,
kilowatt.
10 kilowatt.
Okay.
To
Okay.
model the motor, in actual motor, frame will be grounded and parasitic capacitor will be there between motor frame and primary windings. So leakage current
Mm.
will flow through that capacitance. My question is, some papers show leakage capacitance and small resistance in the leakage path.
Mm.
Do we have to use
Mm.
resistor and capacitance in hardware between star point of RL load and ground to model the leakage currents?
Yeah, I feel it is important because in real life you will not have a parasitic switch off which are giving the 90-degree phase shift. I have measured, I have modeled. One method you can try to model is have a pi network equivalent. You measure if you have a network analyzer with you, model it for common mode impedance and differential mode impedance. Consider that as the two-port network, one winding to the other winding from the ground. Say you connect the star point of short the both the star point. Consider that as the two-port network with reference to the ground, and feed this. Take the input and output parameter and categorize what is the impedance in between. You can you will come up with a good LC network. You have to definitely consider the resistance because in my this thing I have done it for 2 kilowatt motor. We had come up with the RC model only, not the only capacitance. See, it is easy to mention the capacitance. That's why we mention only capacitance. Of course, pure capacitance, pure resistance, it's not there. And inverter side, in general, we don't like to ground the inverter as a whole. Heat sink. Sometimes heat sink even won't be grounded. Frame only would be grounded. If you made an entire converter on the heat sink, you will have a common frame outside, even the frame only to be grounded. Suppose even you don't do the grounding also, the entire grounding avoided also, somehow it formulates the part. So you have to, the main question I assume it is for whether to consider the capacitance alone or to consider the resistance and capacitance also. There are many EMI models available for inverter as well as motor. If you want, you can mail me. I'll email the reference papers related to the modeling of the motor and inverter.
Yeah, yeah, please, ma'am. If you could able to share your mail ID, that will be useful for them. You can just type it in the chat box so that it will be visible.
Okay, I think okay, I have to
Otherwise,
come out of
no
the.
problem. Otherwise, I'll share it. I'll share it. No issue.
Okay, sir. Yeah. Mm.
There is another question on this. Actually, couple of questions asked by the same person. Is there any relationship between number of switches with EMI analysis? That's the first question. Second one, what is the impact of EMI when we connect switch in series than parallel? Example, EMI in buck or boost or buck boost.
Okay. So basically, there are two aspects in here. Suppose if you take an inverter, you have a three legs, correct? Each leg will act as a source. You have from one switch, so number of switches brings in the number of controllability for the converter. You have a three sources will act in three different way. Automatically your sources are going to be different if you are bringing in lots of switches, because your switch will be switched based on your interest in the control. Say in a three-phase leg, first phase leg and second phase leg, third phase leg will have a 120-degree phase shift. Yes, so automatically the sources and the high frequency sources are also will have go through some of the phase shift. So the currents will automatically would be different even if you have a same impedance across the phase legs. The sources would be different. If you put so many switches, the sources would be different. If so many switches are connected in some form, parallel or series, you will have a change in impedance of the switches. Say, for example, you have a drain source and gate terminal of the MOSFET. When you switch on, only some of the capacitances would be connected. Then you switch off, only some of the capacitances would be connected. So the basically you would see the change in the impedances of the converter if you are connecting it in parallel or series. So impedances would be different and sources would be different. Depends on your control.
Thank you, ma'am. I think there is another question continuing with the previous answer, not the previous to previous one. I hope the other one maybe. Yeah, I'll read it out. In continuation, in US and other developed countries, for example, the battery charging is already at the home being connected. Does that mean either they have already taken care of EMI mitigation or the EMI issues may be already affecting these home owners?
So no, actually they would have taken care. Main reason is any product you sell it, first thing they would see is how would it affect the grid. As a grid supplier, as a common, we are connecting everything to the common grid, right? So definitely it would have been done. They would have done some, adapter you are connecting, correct? There will be some EMI filters would have been inside.
Okay,
But
okay.
the effect would be minimal. You instead, standards definitely they have to meet it.
Yeah, if there any professor want to ask any questions, you can unmute your mic and ask one by one. Maybe Professor Govardhan can ask.
Ma'am, good morning, ma'am. I'm Professor Gordon from
Hello, sir.
ETH. How are you, ma'am?
Good morning, sir. Very nice to meet you after a long time, sir. Fine.
Thank you, ma'am. Ma'am, there is one small question on sensor integration. Right now, okay, all the electric vehicles have got so many sensors integrated in the system. And right now, the framework is not being well matured. Okay, there are a lot of things coming in every day for the sensors and the e-vehicles platforms. And with
Yes.
high frequency inverter couplings, okay, they're bound
Yeah.
to get into frequency range of sensor operation. Sometimes it will
Sir,
happen.
sir,
Sir,
your voice is so much
yeah, yeah, it's breaking. It is. Can you
it's
please?
breaking.
Yeah, okay,
Yeah,
is
yeah,
it clear
it's
right now?
better. Better
Now
now.
it is clear. Now it is clear. Please,
Yeah.
better.
Okay. Okay. Regarding the sensor integration in the electric vehicles, okay,
Mm.
most okay, we got okay, a lot of sensors okay, working in typically in order of kilohertz to megahertz range, okay, in operations right now. Okay, right from
Yes.
okay fuel okay to the okay motor drive control. So, but
Mm.
these frequencies are typically lying in the range of your inverter based operations very commonly. And
Yes.
there is
Yes.
bound to be a lot of interference okay basically from high current high power applications on
Yes.
these
Yes.
low power okay applications okay devices.
Yes. Yes.
So
Definitely.
okay, and even though we have an okay predictive shielding mechanisms already in place, but
Mm.
the spikes etc are not okay highly predictable. So what
Mm.
is okay mitigation from your end? Okay, even though we have got sensor based mitigations, okay, what are
Mm.
mitigations there from power electronics okay side to prevent these AMIs leaking out from your systems? Because okay,
Okay. So,
and okay, say in ABS we'll have an okay sensor okay very close to your okay power electronic drives.
mm.
How do you mitigate those in
The
those real conditions?
first thing in the control side, what people do is first they filter out. Once the measurement is done, they will try to, because our information we need is at very low frequency. People try to filter out first all of the noises. When you any control you take it, the first processing will be filtering from the control perspective. In other perspective, suppose if you make any system, first thing what we try to do is modify and measure whether the noises are within the reasonable limit at all of the points you are having an interest, say at the output or at the input. You measure first when you install it itself. So you say you are making a system, either a person who is making an electric vehicle, once they have a layout, they will have a layout where to place everything, how to ground everything. First, they should have, matured already enough to make where to place the components even. If you change the place of component, the noise will be different because the propagation path would be different. So when I consider overall system as a design person, first I have to try to reduce my all of the noise source, the paths. You have to try to minimize the EMI path first by designing appropriate grounding for your system, by appropriately placing your component, and with the proper usage of shielding. Say for example, if I connect inverter with the motor just without shielding, and with shielding there will be lots of effects different. So, as a design engineer, definitely people have to look at rigorously how to minimize these EMIs. It would have been done already amazingly by each of the companies, say Semicron or different people. Inverters, they would have made it very nicely without much of parasitic inductances and capacitances. And when you make the system, you have to make sure further how to reduce all of these parasitic. After that, control side has to take care of how to minimize it further. So each and it's not that one particular solution I have to look at it to reduce the EMI. I have to look at all the possible sources, all the possible ways to further reduce. Otherwise it will burden one solution more. Say for example, I am not minimizing my path properly, I am not optimizing my ground paths properly, and then it will add on your effort on your filter. So yeah, I just didn't do anything. I just made my system and I measure it. I'll just increase my filter size, right? So I have to make sure in all possible ways, all possible. Each source contributing to the noise, I have to try to reduce. Each path contributing to the noise, I have to reduce.
Thank you. Thank you.
Yeah.
Any
Thank you, ma'am.
Yeah. Can we take one more question only? Rest
Yeah.
of the questions I can
Sure.
answer through
Yeah. Through
email.
mail I can send. Sure, ma'am.
Yeah,
I'll
yeah,
take up all the questions, other questions, and I'll send it to this concerned people or to everyone. I hope one more
yeah.
question has been posted. What are the best measuring instruments for precise measurements?
So R&S is the main, you could say in India, the main standard persons making compliances and other things. So R&S I would suggest. But the only difference is R&S is too costly. Any measurement setup you are looking for, it's too costly. So if you are trying to measure at the laboratory level, I would suggest we can even go for. I am using Keysight Technologies, LASIN. They have, of course, bought it from some other company and gave it to us. We bought the spectrum analyzer of similar standards of R&S from Keysight.
Thank you, madam. Thank you for the wonderful.
Hello.
Yeah,
Yes. Yes.
please,
Yeah.
please go
Hello,
ahead.
ma'am. Karthik
Yeah,
here. So we are
please.
into basically measurement of power quality and EMI noise interferences, etc. So we
Sure.
use field type Minsky. We carry mobile instruments. We use in field. So is it
Okay.
handheld what you suggested? I mean, are these
I didn't
instruments
get
all
you. You
handheld
use
kind of?
mobile instruments to measure, is it?
I mean, we have I mean, it's a portable instrument, rather mobile, not mobile. It's a portable.
Okay.
So, what are the base instruments like Class A or Class B kind of instruments, which is
Okay,
in the
okay.
modest cost available? I mean,
See, it
day-to-day
depends on
use.
your this thing. What is your each standards meeting? You should have a conditions for each of the precise measurement of the system. Calibrated system, you have to check whether is it as compiling with the actual standards measured. See, ultimately, any product you make it has to go through the standards for particular thing, whether class A, class B, or class C, or industrial. Say for example, industry applications doesn't require much of EMI standard, but household appliances and electric vehicle CSPR standards are strict. So whether that will have a proper precise measurement or not depends on you could say the application. Say for example, I am measuring the 5 ampere current. Okay, I am measuring the 5
Okay.
ampere current at 50 hertz. What is my bandwidth required maximum? What is the accuracy required maximum? This is what I would look at it, correct? So similarly, any
Yes, yes.
measurement you see it, what is the maximum bandwidth of your measurement? At least you should have a 10 times higher, you could say in the layman term, 10 times higher bandwidth, and accuracy you should have. See, if I have to measure 0.01 ampere, definitely my
Okay.
accuracy and precision has to be little bit higher than that.
Okay, ma'am.
Thank you. Thank you.
I got it.
Thank you,
Thank
everyone.
you. Thank you. Thank you, everyone.
Okay, thank you so
Thank you,
much
everyone. Thank you, every
for giving me
participant.
this opportunity.
Yes, madam. Yes, please.
Yeah, that's it. I'm concluding.
Thank you so much. Dear participant, madam is very approachable. I already shared mail ID. You can clarify any doubts with her through proper.
No, you can share the
Yeah.
presentation also. I saw some of the messages coming. They want
Sure,
the
sure, sure.
presentation. You can
Yeah,
share it with them.
I'll definitely share the presentation along with the certificate. It will take a couple of days, another couple of days. Please be patient. And thank you again for joining. And please be connected such webinars from such intellectual. It is really useful. Thank you for participating, madam, once again. Thank you all.
Thank you, sir.
Thank you. Thank you, everyone.